Hello, I'm Ria, and this is my submission for the Machine Learning Foundations for Project Managers assignment. As part of the assignment, we need to predict the net hourly electrical energy using observed readings. What we have are labeled existing observations, a single numeric output is required, and there are multiple features that could impact this output. So my approach for this problem is to use parametric regression with supervised learning since we have labeled observations. And the performance metric that I've chosen is mean absolute error. It's a direct metric. It's easy to interpret since I can just say that my model is off by this much or this many or this much data, and it's easy to perform in Excel. That's why I've selected this metric. Moving on to feature selection, I have used correlation to see if I can determine if there's any relationship between the features and output. Judging by my results, it seems that temperature has a minimal relationship with exhaust vacuum, and there is a very small relation between the output and ambient pressure and relative humidity, but nothing conclusive. So I can't say for sure that these features will positively or negatively impact my predictions. Now, moving on to algorithm selection, I'm going to use Excel for my model building that has made an impact on which algorithms I've chosen. Linear regression seems to be the obvious solution here because we have labeled observations, we have multiple features, we can get an intercept and coefficient and make predictions using an equation. And I'm going to create different models by using different combinations of features involving single and multiple linear regression. Another factor is, of course, it's easy to perform linear regression in Excel, so that's why I've preferred this method. I did think about decision trees because we have multiple features, and using a decision tree, split the data set based on the best feature and then keep splitting until either minimal number of samples is met or there's a maximum depth of the tree reached, then generate predictions using the average of observations at the leaf node. So this is another model that can be used for this problem. Now, as part of the modeling, I split my data into 90% training, 10% test. Out of training, 70% is used for the actual generation of the coefficient and the intercept, while 20% is for validation to ensure and to judge the performance. So what's my feature or model split looking like? I am going to have models for single features, only temperature or only relative humidity or only ambient pressure to generate predictions. I'm going to use a combination of features, 2, 3, and I'm also going to use all 4 features, see the result. There's also an interaction term model where there are the 2 terms that are related to each other, however minimally. I'm going to use them to generate predictions. And these feature combinations were generated using the factorial method. The steps that I performed for my regression is I have multiple models. For each model, I created an equation, used training to get the intercept and the optimal coefficients, then used the generated regression equation on my validation data set to get predictions. I then calculated the mean absolute error and recorded the score or the MAE of each model. Once I completed these 5 steps for each model, I would then compare the MAE and use the model with the lowest MAE on my test set. That's my final model, the one with the lowest MAE. A brief look at the equations that I have. So these are my 2 feature models, and these are the equations using the regression. These are the actual equations with the intercept and coefficient values. These are the results. As you can see, the model with the least MAE is temperature and exhaust vacuum. On to 3 feature models, not faring much better. Temperature, relative humidity, and exhaust vacuum has the least MAE here, and it's a combination of 3 features with an intercept and coefficients. And the remaining models are the single feature models, so not bad, but not as low as the 3 feature model. And the interaction term model, where these are 2 features that are actually related to each other, it's not a great MAE. all four features is lower than that. So this goes to show that correlation really cannot accurately predict how accurate, how good, how good the model would be, even with features that are related to each other. So now that I have all models executed and MAE for each one of them, I ranked the models based on their MAE, starting with the lowest one, and easily you can see that temperature, relative humidity, and exhaust vacuum is the model with the least MAE, hence this has to be our final model. So I've recorded a short demo of my, performing the regression using this equation on my test data set to generate the predictions. So let's watch that video. So here I'm going to demonstrate how I perform linear regression in Excel. I have my equation for the model over here, where three factors are going to be considered for calculating the electrical energy output: temperature, relative humidity, and exhaust volume. I have those three columns over here. This is my final model equation with the coefficients that have been derived from training the model in Excel. And I have around 957 records in test over here. These are records that haven't been used in validation or in training. So this is the first time that the model is seeing this data. Let's see how it predicts. I'm going to make a column here for calculating the predictions, and I'm going to copy the formula or the equation. Using the power of Excel, I am going to calculate the first prediction. Relative humidity is in column C3, exhaust vacuum is in column 3. Okay, and let's do the same for 957 records. Now, these values have a lot of decimal places. The observations or the actuals are rounded to the nearest two decimal places. So I'm going to do the same in order to keep the calculations consistent. I'm going to use Excel's round function to round my values. Again, do the same for 957 records. And then, now these are my final predictions. So let's write final predictions. I have my actuals, I have my final predictions. I'm going to calculate MAE, or mean absolute error, starting by calculating the difference between actual and prediction. So let's take B3 minus F3, and it's negative because, yeah, the prediction is greater than the actual. Let's repeat the same for all the records. Once we have the difference, we need the absolute value. Again, using Excel, let's calculate the absolute of G3. It should give us a positive value. Repeat for 957 records. And now with the absolute, to finish the MAE calculation, I need number of observations and I need the sum. So number of observations is 957 minus the first two columns, which are header columns, plus 957, and the sum of all these columns is going to be H3 up till H959, because it's going right to the end. It should give us the sum. So we have the sum, we have number of observations. MAE is very simply the division of the sum and the number of observations. Yep, that's the division. Let me round it to get a more consistent value, also easier to read. We have an MAE of 3.65. So that means our predictions are 3.65 points away from our actuals, either greater than or less than. And when I compare this MAE with the MAE observed in training or in validation, it was 3.68. So it's very close. So this is the final equation that can be used to the final linear equation that can be used to calculate the electrical energy output. Okay, so that was a demo of my approach on the test data set. So in summary, these are my final conclusions. The final model that I used involved temperature, relative humidity, exhaust vacuum. Three features contributing to the generation of electrical energy predictions. My test set consisted of 958 records with the performance metric of 3.68. So very close to the MAE recorded on during validation. And that means that my predictions are off by 3.68 megawatt give or take. This is also my final equation. In summary, I would like to say that this was a great learning experience. Performing machine learning on a data set and generating the results and seeing the problems that can occur was a great learning experience. And thank you for watching this video. And I hope you learned something from it. Yeah, thank you.